What's cracking, guys? The idea of this video is going to be extremely ambitious. I'm going to try and give you the most seminal and important ideas for how to scale your models up to scales of hundreds of billions and even trillions of parameters. So I'm going to cover multiple papers, as you can see here. So we have Megatron-LM from NVIDIA here, introducing the tensor or model parallelism. I'm going to walk you through quickly through pipeline parallelism idea from the GPipe paper. I'm going to walk you through the data parallelism idea, which is probably something most of you are already familiar with, but just to round them up, I'm going to cover that one as well. I'm going to quickly go through the mixed precision training paper as well. And finally, I'm going to go through the ZeRO optimizer, so the ZeRO redundancy optimizer from Microsoft that enabled training models up to 1 trillion parameters big. So why should you care about this video? Well, the thing is the following. So if you ever want to train a model that's bigger than, let's say, if you're dealing with, say, GPT style of a model, transformer, if you want to go like above 1.5 billion parameters, you literally need more than 32 gigabytes of VRAM, which most of you do not have. So up until basically 1.5 billion, a single GPU with 32 gigabytes of VRAM can handle that training if you don't have any of these optimizations. Other than that, it's impossible to train bigger models. So combining all of these ideas, you'll be able to literally train super big models. Some of them you must have seen recently published models such as the BLOOM from the BigScience organization, and also Opt175B model from Meta. So all of those models are like hundreds and hundreds of billions of parameters. Other examples are like Chinchilla from DeepMind, Gopher, Palm. So yeah, guys, before we go there, I want to make a quick shout out to AssemblyAI and thank them for sponsoring this video. Basically, they offer a super powerful speech understanding and transcription API. You can see how easy it is to get started in Python. So literally a couple of lines of code and voila, you get your transcription back, as well as in this case, sentiment analysis. They offer various other understanding features such as entity detection, etc., etc. You can also check out the no-code solution, although I guess this is not that interesting for most of you. But if you just want to quickly understand the features they support, you can check out this page as well. If you are struggling to get started, which I doubt, because it's super simple. There is even a tutorial, very detailed tutorial on how to get started. And if you like ideas for projects, they have a YouTube channel with cool videos such as this one, which is like literally 30 minutes long, explaining how to summarize various podcasts with their API. So that's very cool. Finally, they have a very cool set of blogs in general and tutorials on how to get started with various other models such as DALL-E. So yeah, I think that's fairly cool. So give them a go, support the channel. I'm linking the free API token down in the video description so you can use it and get started in a couple of seconds, literally. You get, for the toy projects, you have no problems with the free account. You get $300 of transcription. If you want to upgrade, you can always do that. And having said that, let's go back to the video. So first, let's start actually with data parallelism, because that's probably the simplest idea to explain. The idea is the following. So you have a neural network, and what you do is you literally take the weights of your neural network and you just replicate it. So you copy paste those weights across multiple devices. So you have like, let's say n GPUs, and you literally copy paste that same network across all of the devices. And then what you do is you take a batch of data. So you basically take a batch of data. So it's going to look something like this. So literally you have a batch of data here. And what you do is you split it into multiple parts. So let's assume here we just have 3 devices. So that means you're going to split the batch. So this is the batch dimension, by the way, this here. I'm going to simplify it, like just going to represent the input tensor as a 2D object, even though it's usually going to be, depending on your data, 3D, 4D, whatnot. So you grab the first chunk, the first part, and you feed that into the first device here. Then you grab the second chunk here. You grab the second chunk, and you pass that second chunk of data into the second GPU, GPU 2. And finally, you grab the final piece here, and you pass that one here. Then you do a forward pass through your network. So you're going to do a forward pass here, forward pass here, forward pass here. and then you calculate the gradients. So now what happens is that all of these devices have different gradients as a consequence of you feeding different parts of your input batch. And now we just need to basically reduce all of those gradients. And when I say reduce, I literally mean you sum them up and then divide by the number of devices to get the average gradient. So there are multiple ways how you can implement this. In this particular image, there is this thing called parameter server. So you do the basically reduce and scatter operation. So you grab all of the gradients. You're gonna send the gradients here. So you're gonna send. And by the way, I'm sorry, I'm kind of glitching with this like highlighter here, but hopefully you can see what I'm doing. So we send the gradients here. We send the gradients here. We send the gradients here. We do the averaging of those gradients. And then you literally, so in this particular implementation, the weights are updated directly on the parameter server. And then you do the scatter operation. You literally send back the new weights back onto your devices. You send back the weights, okay? And that's how you achieve training with a much higher throughput, because you can imagine here, although there is some overhead, obviously, you literally have 3x higher throughput compared to if you were to train on a single GPU, okay? And when I say GPU, it can be a TPU, it can be arbitrary device, basically. So what's the problem with this idea? The problem is it's the underlying presupposition here is that all of these networks can fit into a single device, which is the problem, because we know that our models are much bigger and usually cannot fit into a single device. So what do we do then? Well, then we do like things such as model parallelism. So I'm going to show you the first. So that's the data parallelism. And I'm going to show you the model parallelism idea. So this is a seminal paper from NVIDIA called Megatron-LM, training multi-billion parameter language models using model parallelism. It's literally the idea behind both BLOOM, both Opt 175B from Meta. I think some of the EleutherAI's models were also backed up by Megatron, at least implicitly, because I think they're using DeepSpeed and GPT-Neo-X codebase, and DeepSpeed basically leverages Megatron in the background. I could be wrong here. I'm fairly sure this is correct. Anyways, let's dig into the paper. So they say here, this is called intra-layer model parallel approach. I want to contrast that quickly, and I'm going to explain this in a bit more depth a bit later, with the pipeline approach, which is the inter-layer splitting. So the difference is the following. So imagine you have a transformer, and I'm going to be using transformer as the running example. So imagine you have a transformer here. The main difference between these two approaches is the following. So you have n layers here. So you have m blocks of your transformer, and the pipeline approach does the following thing. You literally grab, let's say we have 4 devices. If we have 4 devices, then we're gonna do the following. We're gonna take the layers 1 through 4, and then 5 through 8, and we're gonna send them onto separate devices. So that's the pipeline approach. So you literally take this, and you put that onto a separate device here. Then you take this one and you put it. So let me draw it here. And I'm literally not explaining the pipeline idea, so I might as well explain it the whole way. So literally, you take the layers 5 through 8, and then you feed them into the different device here. And then you take the layers, the next 4 layers, because I don't know how to add. I'm just gonna use the, yeah, whatever. So literally, you feed that into the 3rd block, and then the last one. The last 4 layers are going to be fed into the last block here. Okay, so that's what the pipeline parallelism approach does. It literally splits the model, so-called. Well, I think this is the horizontal splitting, and you can now imagine that each of these devices needs to hold literally 4 times less memory, roughly. I mean, at least when it comes to weights. There is also the optimizer states, etc., etc. Okay, so the idea on the opposite side here with model parallelism from the Megatron-LM paper is instead you're splitting, you're doing the so-called vertical split. So you do the following. You instead, let me take some colors such as green. And let's imagine we have just 2 devices. It's going to be easier to draw. So you literally split your transformer like this. So literally vertically split it, and then you send this piece here onto one device, and you send the other piece, the other half of the transformer, onto the other device. So that's the model parallelism, or the tensor parallelism, as a different name for that same like concept. Okay, because I'm already halfway through explaining the pipeline parallelism, let me quickly go through that. So that's the idea. I think well, one of the papers that mentioned that idea was the GPipe from Google. Others were, I think, like PipeDream or something. There are multiple papers implementing similar ideas. But the idea is, as I mentioned, this one. And what's the problem here? Well, the problem is if you just naively approach training a model that's split using the pipeline parallelism, you have a problem with these so-called bubbles. So let me try and demonstrate what I mean by that. So imagine you feed a batch of data through this pipeline, okay? So you have a batch of data here. I'm gonna denote it as, well, I guess like this, just to make a difference between the layers and the data. So the thing is, while you're doing the feed forward through the first device, i.e. through the first, let's say, 4 layers, the other 3 devices are idle. And you can see that on this diagram like this. So you can see here, you can literally see here that these devices here are idle. So these 3 are doing exactly nothing, okay? There is no computation going on. So that's kind of wasteful, right? And then once you do the feed forward through the first 4 layers, then you basically send the activations to the second device, and you start doing the feed forward here. And at this point of time, the 3 devices, the first and the third and the fourth one, are idle. So you can see here, literally these devices are doing nothing. So you can see here, this is gonna be idle, these 2 devices are idle, etc., etc. And so then you end up, you propagate through all of the 4 devices, and then you start doing the backprop. So you wanna calculate the gradients, and when you start doing that, again, in the backward pass, you're literally waiting. So you're doing backprop here, but these 3 devices are being idle. So this is super wasteful. So there is a simple way how you can avoid this, and it's called micro batching. So you split your mini batch into multiple micro batches, and then you start feeding them into your pipeline and increase the throughput. Let me show you what I mean by that. So you can see the diagram is here, but let me explain conceptually what it means. So here, what you do is you split this input data into multiple chunks, into so-called micro batches, and you feed this first part here. So you feed it here, and while it's running here, and then the moment it starts running through the second device, you immediately feed the second part, the second micro batch, through this device. And now you have 2 devices not being idle. And then as soon as this device passes on the activations to the third device, you can feed the third micro batch into this device, and so on and so forth. You get the point. And you can see the diagram looks like this. So initially, for the duration of the first micro batch, you literally, and let me just change the color here. You literally have 4 devices being idle. So you can still here see that the 4 devices are being idle, which is wasteful. And then only 2 devices are being idle, and then only 1, and finally here you can see that all of the devices are being busy, and you have the 4x the throughput compared to the naive implementation of the pipeline parallelism. So in order to get as many of these columns where all of the 4 devices are active, you want to have a lot of micro batches. And what the GPipe paper showed, basically empirically, is that you want to have m greater or equal than 4k, where k is the number of partitions or the number of devices, a fancy way of saying number of devices. So that means if you have 4 devices, you want to have 32 plus micro batches, and then literally they showed that you almost have linear scaling of the throughput, which is awesome. Okay, so that's one way you can take a huge model, split it across multiple devices. Each of the devices will have only a portion, a slice of the network weights, and thus you can train this whole system faster because you have faster throughput, and it's also feasible in the first place because, yeah, you cannot kind of stick it into a single device. Okay, so that's the second idea. Now let's go through the actual paper. This one is very fun. Let's get back to the first sentence. So we started here. Intra-layer model parallel approach. We now know what that means. So it's intra, we're splitting the actual layer. We're not splitting across layers. We take a single layer and we split it into 2 parts or 4 parts or 8 parts or whatnot. Our approach does not require a new compiler or library changes, is orthogonal and complementary to pipeline model parallelism, and can be fully implemented with the insertion of a few communication operations in native PyTorch. So the cool thing is the complementary part is very important. So this part is super important because that means you can combine these two approaches to scale to even bigger model sizes. Okay, then they say this, we sustain 15.1 petaflops across the entire application with 76% scaling efficiency when compared to a strong single GPU baseline that sustains 39 teraflops, which is 30% of peak flops. So let me kind of break this down. First of all, I forgot to mention here, they're training a model that has 8.3 billion parameters, and they're training on 512 GPUs, okay? So what I say here is that they achieve a throughput of 15.1 peta. So peta is, I guess, 10 to the power of 15 or something. So it's like 1000 tera or 1024, depends whom you ask. Flops is the floating point operations per second. So that means you have this many operations per second. That's a huge number, okay? And what they say is that they have 76% scaling efficiency. So what does that mean in practice? That means the following. Let me open up a calculator here. So we have that the single device, single GPU has 39 teraflops. So if you multiply 39 times the number of GPUs, ideally, this would be ideal scaling, we'd end up with 19 petaflops. And you can see here that they only end up with 15.1, and that's where this 76% scaling efficiency comes into play. So if I multiply this with 0.76, we end up with exactly 15.1 petaflops. Okay, so basically you can see that the GPU baseline has 30% of the theoretical peak. So that the GPU will never have its full it will never reach its full theoretical peak. And then when you additionally scale across multiple devices, you'll never have ideal linear scaling, but it's close enough. So that's cool. Okay, so let's continue here. Let me see what's interesting. We're gonna see how we are gonna split the two particular blocks. So we're gonna see how we split the MLP block first, and then I'm gonna show you, this is probably a bit easier, how do we split the attention block, and they also split the output embeddings as well as the input embeddings. And finally, a detail worth mentioning is that this residual connections, additions, layer norms are actually replicated across devices. So there is some duplication going on. For various reasons, they decided that's the most optimal thing to do. But that's the plan. Let's see how do we vertically break up the MLP, how do we vertically split the attention block. That's gonna be the main gist of this paper. Okay, let's start here. Here you can see the diagrams of how the splitting happens. So the upper diagram here shows you the shows you the MLP block, and you can see this is the first linear layer, the second linear layer, and this is how it's kind of split down. But let me go into the formulas. I'm going to slowly understand how this works. But first, on the high level, what happens here is that you can see that these weights, you take the weights of this linear layer, you split them column-wise, and you keep A2 on one device, and you keep A1 on the second device. So you split the matrix that you use for your feed-forward layer, and you split it into 2 parts. You do the same thing here, but the difference is here you split it row-wise. So you can see here we don't have column-wise splitting, we have row-wise splitting, okay? And so you take B1, you put B1 on one device, you put B2 on the second device. So basically you can see here that all of these operations are happening on a single device, okay? And then there's this G operation going on, which is gonna synchronize the 2 devices. More on that a bit later. And the second device, obviously here, is processing the second part of the MLP, Okay, so it has the A1 and B1. So that's how we achieve the vertical splitting. But that's only a high-level diagram. Let's understand why this works and how is it equivalent to just having everything on the same device. It might be like maybe tough to grasp on the first fly, but it's fairly simple once you think about it a bit. Okay, so here is the implementation. Here's what the layer does. Here's what the feed-forward layer does. You do this is your input data X. This is your weight matrix A. And this is the activation unit value in this particular case. So there is multiple ways we can split. We saw the column-wise and row-wise. Let's see the advantages and disadvantages of both. If we split the weight matrix basically row-wise, as you can see here, then we have a problem. And that problem is we need to synchronize the devices after this pass. So let's see why that's the case. So if we now multiply this, you get x1 times a1 plus x2 times a2, and then you need to apply value. So the problem here is the plus. And that means that the two devices will need to communicate. So that's the only way you can well, add those two separate activations, right? And then you apply the value. The problem is the value is not like is a non-linear function. So value of adding these two is not the same as value of the first term plus the value of the second term. And so they say this approach will require a synchronization point before the value function. Okay, let me try and map this matrix multiplication into the diagram with which you're probably familiar with. Okay. So let's start like this. We have the input data X. I'm gonna assume our batch size is only 1. So we have something like this. So we have X here, and we split X into two parts. So we have X1 and we have X2 here, okay? Next up, we need to pass that through the feed-forward layer. So we have a weight matrix. We're going to multiply with it. So this is going to be just some box here. I'm going to fill in the details a bit later. And we end up with the final representation. I'm going to denote it as a red rectangle here. And that's it, okay? And now I'm going to draw like a matrix A here. And we said that we are going to split the matrix A basically row-wise, right? So you're going to split the matrix A row-wise. So let's see what happens now. So if we multiply this part here, and let me kind of zoom in a little bit here. If we multiply this part here with this part here, what does that mean? So that means that we do the following thing. We literally do this. Whoops, we literally do this. So we do, this is kind of how it's gonna look like if you write if you draw a neural network, okay? So that's what you've done by multiplying this part with this part. And then you multiply this with the second part, okay? So now you multiply with the second piece here, and that second piece is gonna give you the second output. And you end up with something like this. And then you do this here and this here, and you end up with 4 outputs. So I'm kind of using only 4 to simplify the drawing. So the problem is that all of these outputs here are still incomplete because they are missing the contribution from the X2 portion. That's why you have to add the actual representations. So what you do now is, let me change the color into, let's say, red. So now you'll have to do the multiplication between this one and this one to end up with the contribution to the first output element, okay? So this gives us this, and then you just repeat, and you get the contributions to this one, and to this one, okay? So that's hopefully kind of helps you understand how this maps to the neural network diagrams with which you're used to. So as you see, if we just do x1 times a1, we only get partial contributions to the output, and because of that, we also have to add additionally the x to a2, and only then can we apply the value. Okay, now let's go to the second way of breaking down the weight matrix, and that's the column splitting. Okay, so another option is to split A along its columns like this. This partitioning allows the GLU nonlinearity to be independently applied to the output of each partitioned gem. So you can see what's the benefit here. You can literally send X. So this time you're sending not X1 as here. So please notice this thing. This is a very important detail. So here we have X1. Here we have X. So that means we're passing the whole input. And as well here, and here we had X2. So, but the benefit we get here is that we can literally do everything on that device and then apply GLU, and that's it. We don't have any synchronization going on. So that's very cool, because synchronization slows us down. We have to communicate the weights and sum them up and then return them back. Okay, so this is advantageous as it removes a synchronization point. Hence, we partition the first gem in this column parallel fashion and split the second gem along its rows, so it takes the output of the GLU layer directly without requiring any communication, as shown in figure 3a. So that's the hack we're gonna do. So let me now do the following. Let me first show you how the column splitting is gonna look like. So I'm gonna do the same diagram again. Let me just change the color. So I'm gonna do this similar diagram again. So we have our X here. So this is our X. We have something going on here. I'm gonna just draw like this, like a box here, a placeholder, and then I'm gonna pick the red color, so we denote the output representation with red. And let's now multiply the input X, so this is again X. Let's multiply X with our matrix that's split column-wise this time. So that's the main difference. Okay, so now we split it. So here you saw the horizontal one. Here we have a vertical splitting. Okay, so what happens now? Let's go through this. So now when you multiply this with this, you literally end up with a full representation. So this output here has everything it needs. So it's completely has all of the necessary information from the input. Then we do the same thing, and now you can see that basically what is going to happen. Let me change the color maybe to gray. After you keep on multiplying this with this part, with this matrix, you're gonna end up with a half of the output representation vector. But this half is for is going to be actually it's going to contain all of the information necessary. So we don't have to do any summation. That's the advantage here, okay? So we do that on two devices. We end up with these representations. We apply the GLUs, and then we feed. So now this is the nice part. We'll literally just take these representations here. So we apply GLUs again. So we apply the GLU, and we then feed them as X1 to the this layer where we split the weight matrix horizontally. So that's the nice part. So now when you concatenate these two, you get an MLP, and you have literally half of the weights on one device and half of the weights on the second device. That's it. As simple as that. Beautiful idea, if you ask me. Very simple, but very beautiful. And that's drawn here. Again, you can see it here. So we start with X, we replicate X, then we have, because this one is column split, we can just do X times A2, and then we apply GLUs, and then we just feed that here, and then we multiply with B2, and here remember we have horizontal, so row-wise splitting, and then we have the G, which is the synchronization operation, so that means we're gonna sum them up, and finally we end up with the final representation Z here. That's it. That's how we split the MLP layer. Okay, let me see whether there is something interesting here. This approach splits both gems in the MLP block across GPUs and requires only a single all-reduce operation in the forward pass, so the G operator, and a single all-reduce in the backward pass, the F operator. So let me show you how that looks like. So again, we saw that already. So in the forward pass, the only point where we have to synchronize to do the all-reduce is here, the G. And when we go backwards, once we get the gradients here, we somehow have to combine them, right, to get the representations here. So we literally have to, well, I guess just add them and divide by 2. Whatever, we have to have the synchronization primitive there. Okay. Now for the attention part. And I really hope now you're kind of appreciating the whole engineering the infrastructure that goes into these big language models. It's not just like you set like a hyperparameter in your code to from like 5 layers to like 120 layers of transformer and expect everything is going to work magically on a single device. There is a lot of engineering going on. I'm here trying to explain you some of the methods. Okay, attention is a bit easier, I think, in my opinion. So the thing is, you literally take the query matrix, and I'm not going to explain the transformers. Please do check out my transformer video. I'm going to link it somewhere here in case you're not familiar with the details of the transformer model. You take the query matrix, you take the key matrix, you take the value matrix here, and basically you split them column-wise. And each of these columns is going to literally compute the queries for a single head. So we have the multi-head attention. Let's imagine for the sake of argument here that we only have 2 heads. And by the way, that brings me, let me just quickly mention this. So even though we just had 2 here, so we were splitting the so-called two-way model parallelism, you can imagine splitting the weight matrices into much more like, parts. So you can have like a 4-way model parallelism or 8-way, and you can kind of convince yourself that you're going to keep the equivalence. So if we have 8, if we divide this into 8 rows, and if we divide the input data into 8 pieces as well, you'll just have x1 a1 plus x2 a2 plus x3 a3 plus etc until you get to x8 a8, and then you have to synchronize them, and then you apply GLU. So nothing is preventing us from splitting this into multiple parts. Okay, so let's get back to the attention. So here, let's imagine for the sake of explanation, we only have 2 heads, and basically what will happen is that this device up here, so this device up here is going to compute the first head, so the representation for the first head, and the bottom layer, so the bottom part of this diagram is going to compute the second head. And now we have, this is the head 1 representations, and these are the head 2 representations. And then we just feed them here, and this is the already familiar, hopefully, breakdown of the feed-forward layer, where we do the row-wise splitting. And you can see here that we again have to have the G, because we have to synchronize them, and then we get the output representations. Okay, let me try and demonstrate this again with a small diagram, quickly. So we start with input. So let's assume we have batch 1 and sequence size 1. So we literally have a single token. So that's gonna be the easiest case, but it's gonna hopefully make the point. Okay, so here is our input data. X, again, it's a single token. So B, the batch size is 1. S, which is usually along this dimension, is 1. We just have a single token that has some dimensionality, okay? So some maybe H, the hidden dimension. Okay, so what we do is we basically map it using the key, query, and values. So the first device will literally map this one into, let's say, like this. We have the query, we have the key, we have the value, and you can see that it's like twice smaller dimensionality compared to the input one. And now you're literally gonna do your magic of the transformer, and you end up with the final representation, which is again 2x smaller. So this is H2. If this is H, this is H2, okay? And you just do the same thing on the separate device. So you'll do the same logic. I'm just gonna kind of do it like this, and you end up with the same, well, it's gonna be a different representation, but the same structure here. So we end up with this, H/2, okay? So now we pass those tokens, we pass them here into the feed-forward layer. We do the multiplication. So now we literally have the same example with x1 and x2. So we split our data into 2 parts. That's what we've done here. And now you literally do the, when you multiply with b1, you're gonna end up with this. So let me change the color to like blue. So you're gonna end up with this. So something like this, blah, 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 blah. So we end up with the full representation again, H. But if you recall, we literally have a partial representation. So we'll have to add up on top of this one the mapping that we get from, so the representation that we get from this representation here. So now we'll have to add up this thing here. And only now do we have the full representation. And that's the G operator here. So hopefully the idea is clear until now. That was the main idea. Let me kind of walk you through the text here. So partitioning the gems associated with key, query, and value in a column parallel fashion such that the matrix multiply corresponding to each attention head is done locally on one GPU. This allows us to split per attention head parameters and workload across the GPUs and doesn't require any immediate communication to complete the self-attention. That's very important. We don't need any immediate communication, okay? So this approach for both the MLP and self-attention layer fuses groups of two gems, so general matrix multiplies, eliminates a synchronization point in between and results in better scaling. So what I mean by that is you can see here in both of these diagrams, you can see that we have a general matrix multiply, and then something happens, and then general matrix multiply, and compilers are smart enough to optimize this, to fuse these operations together so that you literally have a single matrix multiply or something. I'm not super familiar with those low-level details. I've never had to do that, but that's my understanding at the moment. So that's what they say here, and this results in better scaling. This enables us to perform all gems in a simple transformer layer using only 2 all reduces in the forward path and 2 in the backward path. Again, that's because the transformer layer consists of one attention. We have a single all reduce here, and then we pass the data that comes out of here, we pass it here, and then we have another all reduce here, the G. So that's 2 in the single pass through the transformer layer. Okay, guys, that's pretty much it. Now, I did say that they also have to split the output embeddings, the input embeddings, etc., etc. I'm just gonna kind of rush you through this. The logic is very similar. I'm not gonna bother explaining this one. We parallelize the input embedding matrix denoted as E, and then the subscript is H, the hidden dimension, and V, the vocabulary size, along the vocab dimension, so E1, E2, column-wise. Since each partition now only contains a portion of the embedding table, an all reduce, the G operator, is required after the input embedding. So again, we'll be able to split the E matrix, which is usually huge, like the vocab can sometimes be like 50,000, etc., etc. So you can split it into multiple pieces, send each of those pieces onto the GPUs, then you do the mapping, and then you'll just have to synchronize. Again, same idea as what we saw before, okay? Then they also mentioned for the output, it's a bit more intricate, so blah, blah, blah. If you just do it simply, then it's super expensive, but then they say, so however, for this case, the all getter will communicate B times S times V elements. B is the batch size, S is the sequence length, and V is the vocab size, which is huge due to the vocab size being large. To reduce the communication size, we fuse the output of the parallel gem with the cross entropy loss, which reduces the dimensions to B times S. Communicating scalar losses instead of logits is a huge reduction in communication that improves the efficiency of our model parallel approach. Okay. And finally, they mentioned this. So those are the almost all of the pieces that make the transformer, but there is also the residual connections, the layer norms, all of that. So let me just mention that briefly. Rather than having one GPU compute part of the dropout, layer normalization, or residual connections and broadcast the results to other GPUs, we choose to duplicate the computation across GPUs. I encourage you to read at your own pace why this is the case, but I think you got the gist of this paper already. A couple more details before jumping to the mixed precision training, so you can understand and appreciate why we need that method. Let me just kind of go here. So to train our models efficiently, we utilize mixed precision training, as I said, with dynamic loss scaling. We're going to learn what it is and why we need it. And then you can see a bunch of details, like how do we initialize the model, how do you scale it, you do some norm clipping, blah, blah, blah. A lot of engineering going on here. Lastly, to better manage our memory footprint, we utilize activation checkpointing after every transformer layer. This is a super important idea. I'm gonna briefly explain it here because it's used all the time. So activation checkpointing, you'll hear this concept being thrown around all the time. So the idea is the following. Again, we have a transformer here. okay? So it's a big model. It has a lot of layers. So now you do a feed forward through that model, okay? So you do a feed forward through the model, and you keep on collecting the activations, okay? So each of the layers will be storing the activations. Why? Well, because when you do the backprop, in order to calculate the gradients, you need to have activations of each of the corresponding layers. So you can already probably notice the problem with this approach. You're literally storing bunch of data here, here, and as you're progressing through the network, the memory peak, so the memory consumption is rising. So the idea with the activation checkpointing is the following. It's very simple, and it's a beautiful idea. It's covered in one of the other papers. I obviously don't have enough time to cover it, but if I get enough requests, I might cover it in the future, merged with some more advanced techniques that came after all of these papers I'm explaining in this video. So the idea is fairly simple. Don't store activations for every single layer, just checkpoint them. So basically, let's imagine we have four layers, okay? And instead of storing activations for all of the feed forward layers inside of the block, you just store the activations at the end of the block. So you literally just store the ultimate activations, okay? So just the activations that are at the end of the transformer block. So you just store these ones, okay? So you just store these ones. And now when you're doing the backprop, so now let's see what happens when you do the backprop, okay? So you start doing the, let me change the color into maybe gray. So we start doing the backprop here. We are good. Now we hit this part where we don't have the activations, and what we do is we just recompute them. So now we trigger the recomputation from this checkpoint here, okay? So we trigger the recomputation from here, and then we can continue our backprop. And then we hit this part here, no activations. We hit the recomputation again, and we end up with activations. Obviously, this is going to happen in a bit more clever way. So while you're doing the backprop, we're triggering the recomputation so that we don't have to wait. So all of those optimization details, but this is the gist of it. This is how the activation checkpointing works. Okay, hopefully you can appreciate that. Now, let me quickly walk you through a couple more details and we're done with this paper. So our infrastructure is optimized for multi-node deep learning applications with 300 gigabytes per second bandwidth between GPUs inside a server. So that's important via this NVS switch, and 100 gigabytes of interconnect bandwidth between servers. Okay, that's important. So we have 300 gigabytes per second between the GPUs, and we have only 100, a smaller number, that's the whole point, between the servers. So why am I mentioning this? The reason being is, you want, when you're doing the model parallelism, because you have all of those all reduce operations, so the synchronization points, you want to have those synchronization points happening inside of a server where the bandwidth is super high. Okay, so that's why when you have a cluster where your node only has 8 GPUs, you don't want to go more than 8-way model parallelism. You don't want to go 16, because if you have 16, then you have 2 servers communicating during the synchronization points, and that sucks. Okay, so hopefully that makes sense. Now let me show you some results they achieve. You can see here that scaling from 1 to 2 to 4 to 8 GPUs, you can see that the efficiency kind of drops, but not significantly. So here is the 77% for the 8-way model parallelism, and if you combine it with the data parallel approach, then you have still 74% for 512 GPUs. That's huge. That's huge. I'm going to quickly explain how we combine the model parallelism with the data parallelism. It's a very nice visualization. So quickly, this is how it's going to look like. As I said, because the servers, let's say, have 8 GPUs, basically you're going to do the following thing. You're going to have something like this, and then you're going to slice this server into 8 pieces, because all of the pieces are a single GPU, and they are very densely connected. And so you literally you'll have 1/8 of the model weights here, 1/8 of the model weights here, etc., etc. And now remember the data parallelism. You just replicate, you copy paste these multiple times. So precisely they use the 64 way data parallelism. So you're going to replicate this so that you end up with, let me draw it like this. So you have 8 here. Whoops. So you have 8 here, and then you have 8 here. And you end up with 64 times 8, and that's 512. And this is going to be your setup. So you have literally 64 servers. Each of the servers has 8 GPUs with high bandwidth internally and a bit lower bandwidth externally. So internode versus intranode. And yeah, then you basically do the logic I just explained. So in this particular example, you have a huge batch. You're going to split it into 64 chunks. And then you're going to pass each of the chunks to one of the servers, and then you do the logic we just saw from the Megatron-LM paper with all of the synchronization points, etc., and then calculate the gradients, and then you're going to do the all reduce and update the whole cluster. That's it. Fairly simple. Okay, at least conceptually. The last thing I want to mention from this paper is it came before GPT-3 was published, which is probably the most famous language model and the ML model in general. And they already noticed the trend. Everybody knew already that scaling is leading to better and better performance. So here, by performance, I mean lower perplexity, for example. So you can see the 8.3 billion model has lower perplexity than the 2.5 billion, etc., etc. They mentioned that multiple times. As the model size increases, the validation perplexity decreases and reaches a validation perplexity of blah, blah, blah. We observed the trend that decreasing model size also leads to lower perplexity, blah, blah, blah. Recently, researchers from Microsoft, in collaboration with NVIDIA, trained a 17 billion parameter GPT-2 called Turing NLG using Megatron and showed that the accuracy is further improved as they scaled the model, highlighting the value of larger models. It was super obvious that somebody's going to do it. It just happened that OpenAI was the first one to do it. And yeah, kind of worth mentioning a historical note, I guess. Yeah, they also have contribution of this paper is they show that you kind of have to reconfigure where you put your layer norms so that you can train much bigger BERTs. Otherwise, you have these instabilities. You can see how the model loss explodes if you just use this default BERT architecture. But that's not important for our well, it is. You kind of have to be aware that everything matters. Even the model architecture is very sensitive. If you rearrange something, all of a sudden you cannot train the bigger models, and so on and so forth. Okay, guys. Now on to the mixed precision training. I'm gonna quickly walk you through this one, and then we're gonna dig into the ZeRO paper. One important quick note before this is all the 3 approaches I showed you: the pipeline parallelism, the data parallelism, and the model or the tensor parallelism, all of them can be combined together. They are complementary. And I think it was branded as 3D parallelism. So when you combine all of these 3, you can achieve like huge scales. And then when you combine it with mixed precision plus the ZeRO optimizer, which you're gonna see in a couple of minutes, then you can achieve truly astounding scales. Okay, that's it. Now let's dig into this paper. So a couple of contributions from this paper. So let's kind of read it. Firstly, we recommend maintaining a single precision copy of weights that accumulates the gradients after each optimizer step. This copy is rounded to have precision for the forward and back prop. So this is the first part. So you're gonna literally have 3 components that I want to explain, and then we're done. The second part is we propose loss scaling. We're gonna see what that concept means to preserve gradient values with small magnitudes. Thirdly, we use half precision arithmetic that accumulates into single precision outputs, so that's FP32 versus FP16, which are converted to half precision before storing to memory. Okay, so the idea is fairly simple. Usually when you train neural networks, historically people use the FP32 format. That means a single number literally needs 32 bits. Instead of that, people have shown that you do not need 32 bits. You can have lower accuracy for neural network training, so like 16 works, and that's it. By just having the amount of data, amount of memory that a single number takes, you literally can save a bunch of memory, and still they show in this paper keep the same accuracy, the same performance of the model as the baseline, which uses the FP32. That's very cool. Okay, so why does it matter? Not only do we store the memory, it's also faster on the modern hardware. So half precision math throughput in recent GPUs is 2x to 8x higher than single precision. In addition to speed improvements, reduced precision formats also reduce the amount of memory required for training. That's obvious. I already said that one. Okay. Okay, let's see what's going on. So specifically, we train various neural networks using the IEEE half precision format. Let me quickly show you. I'll link these somewhere below in the video. But this is the format they're referring to. So you have the exponent has 5 bits, the fraction has 10 bits, and then there is a sign bit, and this is how you represent numbers. Like the float 32 is basically obviously has a bigger exponent and bigger fraction. And while I'm here explaining the formats, let me quickly mention the bfloat 16 or the brain float, because it was originally invented in the Google Brain AI lab. And you can see what's the difference. The bfloat has a much bigger exponent. And the main insight here is, for neural network training, you care about the range. You don't care about the actual accuracy. And this significant or mantissa is what determines how fine-tuned your numbers are, whereas the exponent determines how big can you go. So obviously, with bfloat, you can have much bigger and much smaller numbers without getting the overflow, the infinities, or the nans or whatnot. And so basically, TPUs natively support this bfloat format. And like people have shown, like when you take a look at the problems that, for example, Boris Daima training DALL-E Mini had compared to training on GPUs, TPUs basically are much more robust to these divergences of losses because of the bfloat format. So that's so that's basically my understanding. I might be wrong here, but I wanted to quickly mention all of these formats. Now let's go back to the paper. Okay. So now that you know that, let's see what's going on. So we have to store the master weights. They showed for most models this is kind of necessary. So they say here the need for FP32 master weights is not universal, but for the most models they trained, they did need to do this. So here is the idea. You store the weights as FP32, but then when you do the forward prop, the back prop, you do everything in half precision. So you literally do this float to half operation. So you literally kind of convert the FP32 to FP16. Then you do the feed forward. You can see here you start with the activations, which are also FP16. So you can kind of always make sure that's the case because you control your data. So let's say the input is your image. You can literally feed image as FP16 image and then combine that with FP16 weights, do the forward pass, you get the activations, and then in the backward, you do the same thing. The weights are FP16, you calculate the activation grads. From the activation grads, you get the weight grads, and all of those are in FP16, and because of that, you benefit from like a smaller memory, like a blueprint, as well as the higher throughput, as we saw that some modern GPUs basically have higher throughput for FP16 compared to FP32. That's the bottom line. Okay. So this is the schematic how everything works. So they now mention one explanation why they need the FP32 master weights. One explanation is that updates, weight gradients multiplied by the learning rate, become too small to be represented in FP16. Any value whose magnitude is smaller than 2 raised to the power of minus 24 becomes 0 in FP16. And by the way, you might be confused why 24 and not 14. I'm not gonna dig into that, but just Google for the subnormalized, so subnormal or something like that, subnormal values. Just open up the float 16 and float 32 wiki pages. I'm gonna link those down below, and you'll see what those are. So we can see in figure 2b that approximately 5% of weight gradient values have exponents smaller than minus 24. Okay, let me show you what I mean by that. So let's go to figure 2b. You can see here, this is the training when the model is trained in FP32. And you can see that most of the gradients here fall below this magic red line, the minus 24, which is where the representation range of the FP16 ends. And so that means that all of these are going to be rounded to 0, and you lose a lot of information during training, and because of that, the accuracy, the final accuracy for a model may or may not drop. Okay, So that's one kind of idea why you need FP32. There is a couple of other explanations here, a bit more complex to explain here. I'm gonna kind of skip it for now. So worth mentioning, now that you have to store this additional copy, doesn't that blow up the memory? And here they explain that's not the case because the activations are what matters. So even though maintaining an additional copy of weights increases the memory requirements for the weights by 50% compared with single precision training, impact on overall memory usage is much smaller. For training, memory consumption is dominated by activations due to larger batch sizes and activations of each layer being saved for reuse in the backprop pass. Since activations are also stored in half precision format, the overall memory consumption for training deep neural networks is roughly halved. Okay, they are not obviously taking into account activation checkpointing. They just assume that you have to store all of the activations. In that case, this thing that they've just said here holds. But yeah, okay. Now let's go into the loss scaling. This is a second important concept you need to get the mixed precision training to work. Note that much of the FP16 representable range was left unused, while many values were below the minimum representable range and became zeros. Scaling up the gradients will shift them to occupy more of the representable range and preserve values that are otherwise lost to zeros. This particular network diverges when gradients are not scaled, but scaling them by a factor of 8, increasing the exponents by 3, is sufficient to make the accuracy achieved with FP32 training. This suggests that activation gradient below 2 raised to the power of minus 27 in magnitude were irrelevant to the training of this model, but values in this range were important to preserve. Okay, let me break this down for you. Okay, so here is a histogram of basically activation gradient values. You can see what I said, it's shifted outside of the range that FP16 basically supports. So this is the range that FP16 loves, okay? This is this subnormal or denormalized range. So from minus 24 to minus 14. You can see that most of these values are outside of the range. And if you multiply the gradients by 8, you literally shift all of these rightwards, or equivalently, we move the red line here. And now you have all of these being representable in FP16, thus we will not round them to 0. We will not lose this information. And it turned out, they say here, blah, 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 that this particular range here, and you can see there is a lot of data here, was very important to preserve. And so scaling by 8 for this particular model, it doesn't even matter what the model is, just the concept is important. It kind of saved the training. Okay. So one efficient way to shift the gradient values into FP16 representable range is to scale the loss value computed in the forward pass prior to starting backpropagation. By chain rule, backpropagation ensures that all gradient values are scaled by the same amount. So that's an easy way how you can scale up all of these gradients. You just take the final loss, you scale it up by, let's say, 8, and by doing that, once you start doing the backprop, because how chain rule works, you literally multiply all of the gradients by 8, and thus you'll be shifting the gradients into the representable range. This is the main intuition I want you to take out of this paper. And here's the third technique they do. To maintain model accuracy, we found that some networks require that the FP16 vector dot product accumulates the partial products into an FP32 value, which is converted to FP16 before writing to memory. Without this accumulation into FP32, some FP16 models did not match the accuracy of the baseline models. Okay. Also, for large reductions, for example, sums across elements of a vector, they should all be carried out in FP32. Such reductions mostly come up in batch normalization layers when accumulating statistics and softmax layers as well. So both of the layer types in our implementation still read and write FP16 tensors from memory, performing the arithmetic in FP32. This did not slow down the training process since these layers are memory bandwidth limited and not sensitive to arithmetic speed. Okay, again, just an additional detail that needs to be taken care of. Basically, there are 3 categories. So they say here, this is kind of relevant. By and large, neural network arithmetic falls into 3 categories. So the vector dot products, the reductions, and the pointwise operations such as the activation functions. And that they just mentioned for these 2. So they mentioned that for vector dot products and for reductions, you sometimes have to convert to FP32 and do the operations there. such that you can preserve the accuracy. That's it, guys. That's the idea behind mixed precision training. Now let me show you the results. They show that literally baseline, they are almost always even better than the baselines. So here you can, if you just check out these numbers at your own pace, you'll see that the numbers are always a bit better. So it maybe works as like a regularizer almost to do the training in FP16. For some models, as I mentioned, the loss scaling technique was not required for successful mixed precision training of these networks, but for some others it was very important. Let me show you one. So here you can see that mixed precision training, when the loss scale is 1, diverges. When the loss scale is 128, it does not diverge. And they literally show for different classes of models like this again here, language models, machine translation, they always match the baseline when it comes to accuracy. So that's awesome. And the final idea, last but not least, definitely not least, because this is such an exciting paper. This paper is basically introduces DeepSpeed library. You might have heard of it if you've went through any of the popular LLMs. Most of them use DeepSpeed. EleutherAI, I know they use DeepSpeed. Bloom use DeepSpeed. Opt 175B, the Meta folks, I'm not sure whether they used it, but yeah. So it's literally a paper from Microsoft. It's called ZeRO, Memory Optimizations Toward Training Trillion Parameter Models. Okay, I love this paper. Let's go through it step by step. Let's think step by step. ZeRO Redundancy Optimizer, that's what the acronym stands for. We'll see why ZeRO redundancy. They literally have, well, they reduce all of the redundancy when it comes to model states and residual states. We're gonna see what those are, but that's the idea. ZeRO eliminates memory redundancies in data and model parallel training. ZeRO has the potential to scale beyond 1 trillion parameters using today's hardware. ZeRO can train large models of up to 13 billion parameters, for example, larger than Megatron GPT 8.3b. So that's a model that was trained in the Megatron-LM paper, the first paper I covered, and the T5, the Google's model that was 11 billion parameter big, without even requiring model parallelism. So that's a big breakthrough, because now with this set of optimizations, you as a practitioner can literally train models as big as 13B if you have just a single but very good, albeit a very good, like a GPU. But that's amazing. And obviously when you use the actual optimizations, you can scale to much bigger sizes. They have shown indeed that you can scale up to 1 trillion parameters with a small caveat, and that's that it becomes very slow. I mean, very slow. You literally, for some of the models they've shown, you need a year to train it. So that's practically not really practical, but yeah. They train a model of 100 something billion, so that's kind of cool. Okay, so let's dig into it. MP, so the model parallelism, splits the model vertically, partitioning the computation and parameters in each layer across multiple devices, requiring significant communication between each layer. Okay, as a result, they work well within a single node. I did mention this, where the inter-GPU communication bandwidth is high, but the efficiency degrades quickly beyond a single node. We tested a 40B parameter model using Megatron-LM across 2 DGX2 nodes and observe about 5 teraflops per V100 GPU, less than 5% of hardware peak. So you can see it drops dramatically as soon as you start doing the model parallelism across multiple nodes. Okay, then they say this: for large models, the majority of the memory is occupied by model states. This is an important piece of terminology. They're going to be reusing it throughout the paper. So let's kind of stress that. So the model states, which include the optimizer states, such as momentum and variances in atom, gradients, and parameters. So they consider those to be the model states. The remaining memory is consumed by activation, temporary buffers, and unusable fragmented memory, which we refer to collectively as residual states. So again, 2 pieces of terminology, new terminology here. We have residual states and we have model states. And they're gonna address each one of those separately. Okay, so ZeRO DP removes the memory state redundancies across data parallel processes by partitioning the model states instead of replicating them. So that's the main idea. That's literally the main idea of this paper. They're partitioning instead of replicating. I mean, it's simple conceptually, but there is a lot of work that goes into making this to work efficiently. That's important. So I'm going to show you the diagram. I'm not going to explain it yet what this means. You're going to see it in a couple of seconds. So they have a couple of optimizations. Optimizer state partitioning. So when you partition the optimizer states instead of replicating it, then you can do the gradient partitioning, and then you can also do the parameter partitioning. And they show that the memory reduction is linear with dp degree. So that means the number of devices you use to replicate your models across when you do the data parallelism. For example, splitting across 64 GPUs will yield a 64x memory reduction, which is huge. There is a modest 50% increase in communication volume, though. Okay, with all three stages enabled, ZeRO can train a trillion parameter model on just 1,024 NVIDIA GPUs, which is crazy. Okay, this is the main diagram. Let me first walk you through this piece of text here, and then I'm going to basically jump into explaining the diagram. For activations stored from forward pass in order to perform backward pass, we noticed checkpointing helps. I did explain activation checkpointing maybe half an hour ago, but not sufficient for large models. Thus, ZeRO-R optimizes activation memory by identifying and removing activation replication in existing NP approaches through activation partitioning. Again, partitioning. It also offloads activations to CPU when appropriate. Okay, that's another detail that can be done. Okay, ZeRO-DP and ZeRO-R combined together forms a powerful system of memory optimizations for DL training that we collectively refer to as ZeRO. Again, just another piece of terminology. If you ever start playing with DeepSpeed, this might be useful to know. Okay, so let's see what's going on. Here is how the upper row, the baseline, is how your classical, change the color here. This is how your data parallelism works. You have three types of well, you have parameters, gradients, and optimizer states. You can see that optimizer states take the biggest part of the memory. And you can see across, when you do the data parallelism, I did mention that we literally replicate all of these, you copy paste them, and that's super inefficient, okay? You can see that the memory consumed is 2 plus 2 plus k times psi. I'm going to explain what these are in a second. And for, I think they're using some GPT model here, whatnot, they show that you need 120 gigabytes of memory per device. That's huge. So psi is the number of parameters. I think it's 1.5 billion in this particular example. They're using the GPT model, the GPT-2. 2 is because you use 2 bytes. When you use mixed precision training, you use 2 bytes for weights. You use 2 bytes for gradients. So that's why you have 2 plus 2. And then k is equal to 12, because these are the optimizer states. Because we'll see the calculation a bit later, but for atom, k equals 12. And so you have 16 times 1.5b, you end up with I guess, this number. Is that correct? Let me just see whether I messed something up, but 1.5 times 16, wait, I'm not sure. Yeah, we'll see why. Yeah, well, sorry, it's 7.5b, it says here. Okay, that's why we get 120. Now, the first optimization is, instead of having a copy of the optimizer states everywhere, you instead partition it. So you store one piece of the optimizer states on one GPU, you store the second part here, you store the nth part here, and you can see, so sorry, we have n GPUs here, so that's why we're going to have, ultimately, when you kind of combine all of them together, you'll have still the same information as here, right? And then you can do the same thing for everything else. For gradients, you can partition them. For parameters, you can partition them. And you can see how the memory is slowly decreasing. So here we have 2 psi plus 2 psi, because we're not doing the parameter and gradient optimization. But we do save up on the optimizer state. And that's why we have k times psi divided by nd, where nd is the number of devices in your data parallel setup. So it's going to be 64 in their particular case. And you can see how the memory dramatically reduces. So you started with 120 gigabytes, and you ultimately end up with 1.9 gigabytes, which is crazy. I mean, this is an amazing optimization. Okay, let's continue here. This is what I mentioned before. The complete set of optimizations in ZeRO could allow us to run models with trillion parameters on the high-end hardware cluster today, for example, with 1000 B100 GPUs. However, the hardware compute capacity is still too limited, and training time can be impractically long, over a year. So always take with a grain of salt when somebody says 1 trillion, you have to kind of read the fine print and understand the details of the method. ZeRO powers the largest language model with 17B parameters and record-breaking accuracy, Turing NLG. Important to mention, this was literally, I think, a month before GPT-3 was published, which was 10x bigger than this model, which is like a huge. We share ZeRO as a part of our open source DL training optimization library called DeepSpeed. So I did mention this library multiple times. You can check it out, especially if you want to play with big models. By the way, I'm going through these papers precisely because over the next videos, I'll be covering some of the largest ML models out there. And do let me know if you have any suggestions, what you want me to cover or not. Feel free to comment down in the comments. Also, congrats if you sticked up through the whole video until here. Okay, so let's do a quick memory analysis to understand why K is 12, etc., etc. Okay, so a 1.5 billion parameter GPT-2 model requires 3 gigabytes of memory for its weights, if we assume FP16, or in 16-bit precision. Yet it cannot be trained on a single GPU with 32 gigabytes of memory using TensorFlow or PyTorch, at least without any of the optimizations. I assume that PyTorch and TensorFlow now have a bunch of optimizations included. One may wonder where all the memory goes. So now let's see where it goes. Let's take Atom as a concrete example. So the mixed precision training of a model with psi parameters using Atom requires enough memory to hold an FP16 copy of the parameters and gradients with memory requirements of 2 psi and 2 psi bytes respectively. So we've seen that one in the table before. Basically, yeah. So in addition, it needs to hold the optimizer states, an FP32 copy of the parameters. So we know why this is the case because of the mixed precision training. We always need to store the master copy in FP32, okay? And that's kind of gonna bloat up the memory, but it's necessary. The momentum and the variance, so these are Atom idiosyncrasies, and then with memory requirements of 4 psi, 4 psi, and 4 psi bytes. So 4 because here we have FP32, okay? And because of that, if you sum them up, you end up with 12, and that's why K equals 12. So in total, this results in 16 psi bytes of memory requirements. So yeah, that's why you cannot train a GPT 1.5B on a GPU unless you have some of these optimizations. Okay, now they break up the residual memory consumption, blah, blah, blah. They mention for some set of parameters, like if you're using GPT-2 with a sequence length of 1000, batch size of 32, you require 60 gigabytes of memory unless you do activation checkpointing. Then they say here activation checkpointer or activation computation or recomputation is a common approach to reduce the activation memory by approximately the square root of the total activations at the expense of 33% of recomputation overhead. This would reduce the activation memory consumption of this model to about 8 gigabytes. That's a huge saving. Okay, when the size of the model is large, these temporary buffer sizes are non-trivial. Okay, so they go on to say that there are 3 components to the residual memory consumption. So the activations, the temporary buffers, and the memory fragmentation. Yeah, I'm going to skip this one. It's not that vital, but yeah, you kind of have to have these temporary buffers when you want to do some reductions, etc., etc. Yeah, that's too much detail for this video. Okay, let's get some hints why this works. ZeRO-DP partitions the model states instead of replicating them and uses a dynamic communication schedule that exploits the intrinsically temporal nature of the model states while minimizing the communication volume. Okay, so let that sink in, the intrinsically temporal nature. So let me quickly go back to the diagram here. I think that's going to be the easiest thing to do. So the thing is, let's take parameters as an example. So the blue line here. Literally, when you're doing a forward pass, obviously the forward pass is always at a certain point, at a certain layer in your model. and the only parameters you care about are the parameters that are needed to do the immediately next computation, right? So you can kind of discard everything before, and you don't care about everything that's about to come. So they literally explore that temporal thingy, and they in a smart way communicate the parameters, the gradients, the optimizer states, such that you have basically an illusion that everything is already present there. And they kind of mask the overhead by because of certain intrinsic latencies during the model training. I'm not gonna go into much more detail there. So let's go back here. Let's go back here. We're here, I think. Okay, a couple more things, and I think we're done here. The arithmetic intensity ratio of the amount of computation per iteration to amount of activation checkpoints per iteration is very large and increases linearly with hidden dimension, making it possible to hide. So this is the thingy I just said. The data movement cost for the activation checkpoints, even when the bandwidth is low. For very large models, ZeRO can even choose to move the activation partitions to the CPU memory. And then you literally have like a zero cost of memory and in case you manage to mask that transitioning, the movement of the data to the CPU, then you literally you get it for free. So unfortunately, the paper is very textual. Hopefully you got some insight from the diagrams and the things I explained so far. Let me try and read you a couple more things I highlighted, which I think are insightful. So for a DP degree, again, DP is standing for data parallelism of ND, we group the optimizer states into ND equal partitions, okay? Such that the ith data parallel process only updates the optimizer states corresponding to the ith partition. Thus, each data parallel process only needs to store and update 1 over ND of the total optimizer states, and then only update 1 over ND of the parameters. We perform an all gather across the data parallel process at the end of each step to get the fully updated parameters across all data parallel process. Okay, so it's kind of hard to explain everything. I'm going to show you one thing here. So there's this nice wiki page where you can see these collective operations such as reduce, all reduce, blah, 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 all gather, scatter, all to all. All of these are implemented in libraries such as NCCL from NVIDIA. So that stands for NVIDIA Collective Communications Library. So you can kind of check it out. The diagrams here are useful. It's going to help you kind of understand this. But ultimately, someone needs to create, maybe even me, something that visualizes this much nicely so that you can see and understand what's going on. But yeah, hopefully this gives you some intuition. And that's what we are aiming for. Just like have at least the basic terminology and the basic understanding of all of these optimization methods in place. And then you can always read on the documentation of the particular library you're using if you care to learn more. Okay, I'm going to skip all of these here. Interesting piece of theory, but not that practical. They show that because of, we saw these formulas already in the table, but we ultimately end up with 16 psi over ND formula for the amount of memory, which means as ND in the limit of going to infinity, this goes to 0, but yeah, it becomes impractical. But this shows that this has a profound implication. 0 powers DP to fit model with arbitrary size as long as there are a sufficient number of devices to share the model states. But yeah, it becomes, after a certain point, you hit the saturation point, and this becomes very, very slow. Okay, this is the last part. Let me kind of read and walk you through this. It might be insightful. So more specifically, once the forward propagation for a layer of a model is computed, the input activations are partitioned across all the model parallel process until it is needed again during the back propagation. Okay, so what they say here is, let me try and kind of draw this down. So let's say we have a bunch of devices here, something like this. Let's say we have 3 devices, and let's say you just computed, you're currently here in this part of the network, and you computed some of the activations, okay? And then you proceed forward. So after that, you proceed forward. You continue your forward prop here. Okay, so instead of having that checkpoint, so what's usually done, that checkpoint is stored here. Instead of doing that, why not partition it? And basically, why not store the literally, let me change the color. So you instead store only a chunk here. So you only store a chunk here, you store the second chunk here, and you store the third chunk here. So that's the idea. And then once we need these activations again, we just communicate back those activations back to this device so that we can compute the gradients, etc., etc. So that's the basic idea. I mean, now how that happens, obviously there is a lot of computer science going on in the background, algorithms, data structures, all of that, hardware, electronics. But yeah, we have to kind of stop at a certain level of abstraction. Okay, so it works in conjunction with activation checkpointing, storing partitioned activation checkpoints only instead of replicated copies. So that's what I told you here. So furthermore, in the case of very large models and very limited device memory, these partitioned activation checkpoints can also be offloaded to the CPU, reducing the activation memory overhead to nearly zero at an additional communication cost. I did mention this before. Okay, if we checkpoint a single activation for each transformer layer, it will require about 33 gigabytes of memory per GPU just to store the activation checkpoints. But with this optimization, the PA in ZeRO, it can be reduced to about 2 gigabytes per GPU. Because, yeah, if you have 16 of your model parallelism, then you just divide by 16, you get roughly 2 gigabytes. Furthermore, these 2 gigabytes can be offloaded to the CPU, reducing the memory footprint for activations to nearly zero. Okay, guys, this is pretty much it. The paper is huge. Obviously, there is a lot of heuristics in the background, so they mentioned something here. So given model and hardware characteristics, we leverage the above analysis to decide if and when to apply PA and PA plus CPU. So the activation checkpointing, the partitioning of the activation checkpoints, optimization, and the CPU offloading optimization. And the above analysis is something I encourage you to read. But the idea is, depending on like various latencies, they decide whether this is a good idea or not. So there is a lot of details there, but nothing conceptually fundamental that it will lead you to an eureka moment, to epiphany, I guess. Yeah. Okay, guys. Hopefully you liked this video. Let me end up with this nice chart here. Okay. So hopefully you like this video. If you did, please share it out with your friends, with anyone for whom you think would benefit from understanding these scaling techniques. So we covered a lot of ground here. We covered the data parallelism approach. We covered the tensor parallelism approach. We covered the pipeline parallelism approach. We covered the mixed precision training. And finally, we covered the ZeRO optimizer, where we saw how we can basically cut down and do the partitioning of various model states and residual states so that we can train much bigger models, and even on a single GPU. So yeah, do let me know whether you found this video interesting. Leave any feedback down below. Subscribe to the channel, and until next time, bye-bye.